Hey everybody, welcome back. Today we're going to start the first official lesson in a chapter about graphing parabolas and graphing quadratic functions. Today's is going to be kind of an overview of the most basic type of quadratic function. Today's lesson is all going to be about functions. This is a function notation. Don't have a panic attack about that. It's the same thing as the letter y. Y equals something x squared. So you don't have to get bothered by the function notation. It's the same thing as this, even though they'll never write, or they very rarely will write a letter y. They'll usually put function of x just because they want it to make it look like an actual function notation. So, it's kind of like the questions that we used to have in the last chapter, like this, right, where you would have to break it down to what numbers multiplied together equal 12 that add up to equal 7. Except now there's no part B and C, right? It's just the squared and then whatever the coefficient on the squared part is. So just as a quick overview, they're going to give us a lot of definitions here at the beginning. I want to make sure we're all clear. Parabolas, any type of graph where the highest degree is 2, right? Second degree, that's the highest exponent we have, second degree. Anything where it's second degree to the second power is the highest exponent means it's a quadratic function, and that means it takes the shape of this and this, which we call a parabola, right? Parabola. Sometimes it's going to open up, sometimes it's going to open down. We'll talk about when that happens in a second, but the shape is a parabola. All of these, like I just made an example one over here, they will all have a vertex. The vertex is the point either at the very, very top or at the very, very bottom, if it looks like this, the point at the very bottom, or at the very top, where it starts to change directions, right? Instead of going uphill, it switches and it starts going downhill. Or instead of going downhill, it switches to start going uphill. That is called the vertex. So on my example, the vertex is located right here, which looks like is the point 2, 2, right? And so there's going to be one question today, I think, on the assignment where it's going to ask you to fill in this information. The axis of symmetry is very similar to what you did in elementary school math, where they would have you draw that dotted line right down the middle that splits it symmetrically. And so the axis of symmetry on this one would be right down through the vertex. The axis of symmetry always goes through the vertex, and this line is right at 2 on the x-axis, right? I'm here on the x-axis at the point 2. So my axis of symmetry is x equals 2. The axis of symmetry will always be the same as your x-coordinate in your vertex, just as an FYI. So that is the axis of symmetry. The axis of symmetry is the line that you would draw right in the middle to perfectly split it in half. Now, mine isn't drawn the best just because I'm not a great artist, but that is how you find the axis of symmetry. The domain and range, these are the hardest ones, at least for me. The domain describes how far to the left and how far to the right, how much of the x-axis does your graph use? The domain describes the x-axis, all your input values. And in this example, this graph goes forever and ever and ever to the left. It goes forever and ever to the right, because as it gets bigger and wider, it just keeps getting bigger and wider, and it goes down forever. And so this thing goes forever to the left, forever to the right. Almost every single one of these that I will see, or you will see in this class, is going to have a domain of all real numbers. In fact, it might be every single one that we have, because unless somehow it gets turned sideways, even if it goes up or down, they're always going to continue to get wider as they get larger. And so all of these will go to the left forever and ever, and to the right forever and ever. So almost every single one of these has a domain of all real numbers. But the range is where these are going to be different. The range describes how much of the y-axis does your graph use. Because these will go to the left and to the right forever, but they do not go, like my example here in red, it goes down to infinity and beyond, right? But it does not go up. It eventually stops, right? This graph is on the y-axis. It's only from here down is where this graph is located, right? This graph does not go any higher than where I drew that green line. There's no way this graph can ever go above this line because it's the vertex. And so in this example, my graph goes down to infinity and beyond. I really shouldn't have put those arrows on there. Those are kind of annoying. But it doesn't ever get higher than this green line right here. It's going to go down forever and ever and ever and ever and ever, but it doesn't get higher than this line, which is on the y-axis, and it's at 2. And so the range is going to be on the y-axis. This graph is located below 2 on the y-axis, so it's going to be less than or equal to, because it's on the number 2. The range is how much of the y-axis, where is your graph located on the y-axis? And on the y-axis, this graph is located at 2 and below. Everywhere from 2 and below is my range. If this was going uphill, if this graph was opening up, it would be y greater than or equal to. The only thing that would be different is this symbol would be flipped, and it may not be at 2. It might be at a 0. It might be at -3. It could be wherever. Okay. One thing that I've never really seen very much in my other algebra textbooks that our textbook this year describes is they'll give you a few questions and they'll ask you, hey, when is this graph increasing? When is this graph decreasing? And it's not too hard. Just kind of use common sense. And so, like on my example here, you kind of read these from left to right, just like you read a sentence in a book. So I would say this parabola is increasing. It's traveling uphill all throughout this half of it, right? It's going to get all the way up to this point, and it's getting bigger, bigger, higher. We're going up on the y-axis. We're going up. We're going up. So I would say this graph is increasing whenever we are less than, when we're over here, right? Whenever we're less than this number, which is 2. It's increasing whenever x is less than 2 on the x-axis. But then once we hit 2 on the x-axis, now from here to the end of it, it's getting smaller and smaller and smaller. We're going down, down, down. We keep going down and go to infinity and beyond. So whenever x is greater than 2, this graph is decreasing. It's going downhill. So whenever it says it's increasing when or it's a decreasing when, it's basically asking you which half of the graph is it going up, which half of the graph is it going down. When you think about slope, right? Like positive slope and then negative slope. Okay. Hopefully that is a decent warm-up. Let's see what these will actually look like. On this board, we're going to try to graph some, and what I want to do is compare how these will look, because these look very, very simple over here, but you don't have to actually work them all out to kind of know what they're going to look like, right? You don't actually have to draw a little X and Y table and graph every single one of these to have an idea of how they're going to compare to each other. Okay, so this is called the parent function. See how the coefficient is just 1? This is the easiest one you can do. It's the most basic one that there is, and all of the other ones are basically transformations of this one, right? This is the one that is kind of the original, and then we're going to mess with it. We're going to change it a little bit to get all these others. Now, if you don't know how to graph this, that's fine. The best way to graph it is to do one of these little input-output tables, right? I'm going to make this one go sideways. Usually in class, I have them go up and down. Pick the easiest numbers you can think of for the number, for the letter X. I'm just going to pick 0. I'm going to pick 1. I'm going to pick 2. If I put 0 up here in the spot of the X, 0 squared is 0. 0 times 1 is obviously 0. If I put 1 in here, 1 squared is 1, and then 1 times 1. If I put 2 in here, 2 squared is 4. And so if I graph those points, the point 0, 0, 1, 1, 2, 4, whoa, you'll notice I don't have a parabola. I've only got half of it, right? It looks like I have the right-hand side. So basically what I should have done is I should have picked a couple negatives. Like maybe I'll pick -1 and I'll pick -2 just to make it easy. So if I put -1 up here, -1 squared, -1 times -1 is +1. If I put -2 up here, -2 squared, that means -2 times -2, that's 4. And so -1 and 1, -2 and 4. Oh, that was very symmetrical. Okay, here is the basic, the parent function of f of x equals 1x squared. All of the other graphs that we do in this video are going to be basically manipulating this one. They're going to be reflections, not rotations. There'll be reflections, there'll be stretches and shrinks of this basic one. This is the easiest one we can do. y equals x squared, 1x squared, right? If a, this coefficient, if a equals 1, this is what it looks like. Your easiest, your most basic, the parent function, okay? Now, I could do an x and y table for these others if I really wanted, maybe just because this is the very first day we're doing it. I will do one for these. Whoa, handwriting not very good. I'm going to pick a couple negatives. I'm going to pick -1. I'm going to pick 0. I'm going to pick 1. I'm going to pick 2. If you put -1 up here, -1 squared is 1. 1 times 4 is 4. If I put 0 up there, 0 squared is 0. 0 times 4. If I put 1 up here, 1 times 1. Okay, and then if I put 2 there, 2 squared is 4. 4 times 4 is 16. Oh boy, my graph's not going to fit 16 on there. But what I want you to notice is look how much more narrow this one is. -1, 4 is my first point right there. 0, 0. All of these today are going to have 0, 0, the origin. Then we have 1, 4. And then I'm supposed to have 2, 16, which 16 is way off my graph. I can't even fit it on there, right? Look how much tighter, compact this graph is compared to the last one, right? And that is because this number that's usually the slope, it's not technically the slope on these, but the coefficient, the letter a, whatever the coefficient on the x squared is, you see how we went from 1 to 4? And look what that did to our graph. When we changed this a number from 1 to 4, we have taken our graph and we've like pinched it together. This is called a vertical stretch. We've taken that number and we have compacted. We've made this thing much more close together, right? So whenever you change the a number, right? Whenever you change this coefficient to a number bigger than 1, right? Look what happens to the graph. It gets pinched together. Vertical stretch. It's almost like we took this blue line and we stretched it out and made it go inside there a little bit. If this would have been 2, like if it would have been 2x squared, it would have been a little bit as steep. It wouldn't have been quite as steep as this one. If it would have been like 7x squared, it would have been even tighter together. It almost would have looked like the same line. But look what happens if this number is less than 1, right? See how here it's only 1/3? This is smaller than the original one. If I did my little x and y graph for this one, I'll do this one in a different color. I'm going to do -1, 0, 1, 2. Going to put these in here. -1 squared is 1. 1 times 1/3 is 1/3. If I put 0 in there, 0 squared is 0. Let me move my phone back here where you can see the table. 0 times 1/3 is 0. If I put 1 in there, 1 times 1 is 1. Okay. 2 squared is 4. 4 times 1/3 is 4/3. And so if I graph this one, -1 and 1/3, 0, 0, 1 and 1/3, 2 with 4/3. See how this one is going to be, see how this one is much more open, right? It's much wider. And so this is what we would call a vertical shrink. Do you see the difference? And that's the big idea I want you to get today. The most important thing is if you just look at this coefficient, it's called the letter A, right? The letter A, whatever the x squared is being multiplied by, the big idea today, 1 is the normal one. That's what we're going to start with. That's what we're going to compare everything to. If your A is bigger than 1, your graph is going to be pinched together. It's going to be tighter. It's going to be a vertical stretch. It's going to be very, very narrow. I mean, look how narrow that is. I can barely fit my finger. It's about the width of that. If your letter A is less than 1, right? It's a fraction between 0 and 1. Now, all of a sudden, your graph is more wide open. It's more separated. See how far apart those are, the two sides? It's much wider. It's called a vertical shrink because we've taken this number, the letter A has shrunk, right? it has shrunk down lower than 1, right? It started out as 1, and we've shrunk it down to 1/3, 2/5, 3/7, 4/9, 0.75, 0.38, 0.27, right? Any number or decimal that is less than 1 but bigger than 0 is going to look like this, where it's much more wide open, right? That's the big idea today. Okay. Now, all of these, you'll notice, opened up. They all had the origin as a common point. All of these would have an axis of symmetry right here at y equals, or x equals 0. They would all have a domain of all real numbers. All these have a range of y greater than 0. So all that stuff is the same. They're all decreasing when x is less than 0. They're all increasing when y or x is greater than 0. But the only thing that's different is this number, this letter A, right? Now, on all of these, they're opening up because this A is positive, positive, positive. Let me show you what happens when that A is negative. You can probably guess, right? When the A is negative, my title here, graphing it when A is less than 0. So when A is a number less than 0, when it's a negative number, look at all of these, right? Look at our A. We've got -1, we've got -2, we got -1/4, right? All of these are not going to be opening up. These will all be opening, you can probably guessed it, down, right? Let me start with the basic one. The basic one is this. I'm going to make my little table. This green marker doesn't always cooperate. Let me switch to purple. I'm going to put -2, -1, 0, 1, and 2. And you aren't going to have to like draw these tables on every single one. To be honest, -2 squared. Now here's the thing. I saw some people who did my little warm-up assignment incorrect yesterday, and it's because you were doing the order of operations wrong. I saw a lot of people who were multiplying first and then doing the exponent last. Whoa, that's not how the order of operations go, right? Order of operations says we have to do the exponent first. So you're going to do -2 squared, which is -2 times -2. That's 4. 4 times -1 is -4, right? -1 squared is 1. 1 times -1 is -1. 0 squared is 0. 0 times -1 is 0. 1 squared is 1. 1 times -1 is -1. And then that's going to be -4 as well. So if you look at the graph of this one, -2, -4, -1, -1, 0, 0. All these are still going to have 0, 0 on this one as well. But now instead of opening uphill or opening up, all of these are going to open down, right? So we're going to go something like this for all of them. Whoa, all of them over here. Okay, this is the basic one. This is the normal one. Let me back up my, there we go. How about that? That is the parent function for the negative, right? This is a reflection of the one we had on the other board, right? These two are reflections. The blue one on here with the purple one on here, those are reflections because one of them was +1 and this one is -1. Now, I can probably guess what this one's going to look like just by looking at my equation or looking at my function. You see right here, my letter A is -2. -2. So it's still going to open down, but this should be tighter together, right? Because we have pinched this one, we have stretched out this number and made it greater or further away from 0, right? -2. On the positive versions, right, +2 would have been twice as narrow. So this should also be twice as narrow, but it's going to be opening down instead of opening up. Sorry about that. I keep hitting my tripod. Let me go ahead and make my little table here. And like I said earlier, you won't actually have to make these tables on all of them. This is a -2. It looks kind of dumb. -2 squared is -2 times -2. That's 4. 4 times -2, is -8. I don't have that on my graph. My graph only goes to -7. -1, if I put -1 right here, that would be -1 times -1. That's +1. 1 times -2 is -2. If I put 0 in there, 0 squared is 0. 0 times anything. And then these are going to just be the negative versions here. So this one's going to go like -2 with -8. -1 with -2, 0, 0. 1 with negative 2, 2 with negative 8. See how this one is right? This one is narrow, more narrow. It's pinched together. This is also this orange one is a vertical, this right here is this is a vertical stretch. We've stretched this, this letter A to negative 2 instead of negative 1. It's also a reflection of the original one that was going something like, remember the original one that went like this? This is a reflection over the x-axis, reflection on the x-axis, and it's a vertical stretch by a factor of 2. It's twice as narrow, and it's a reflection of the original one that we started with on the other board. And then this last one, I'm not going to make this look too neat up here, but it's okay. This last one is 1/4, negative 1/4. And so just by using what we've seen on the last two, I have a pretty good prediction what this one's going to look like. Because it's negative, it's going to be opening down. So it's going to be a reflection of the original one, right? The original one that we had way up here to start the other board. This is a reflection over the x-axis. This is not going to be a vertical stretch because this number is in between 0 and 1. It's a fraction. This is going to be a vertical shrink. This thing should be wider, right? This thing should be more wide open like the other ones were here. I like to make the tables go like this. I don't know if I will confuse you by that, but I apologize. If I put negative 2 right there, negative 2 squared is 4. 4 times negative 1/4 is negative 1. If I put negative 1 in there, negative 1 squared is 1. 1 times negative 1/4 is negative 1/4. If I put 0 in there, 0 squared is 0, and 0 times anything is 0. If I put 1 in here, 1 squared is 1. 1 times negative 1/4. And like these are always going to be the same answer today. They won't always be like that, but today they will. So look at this one, 2, negative 1. Negative 1 is like negative 1/4 way up here, 0, 0. Look how, look at this thing. I did 3 points and I barely even got below the origin. 3 would have been like, 3 times 3 would have been 9. 9 times 1/4 is 9/4. 9 over 4 is what, 2 and 1/4, right? So this thing is barely even creeping below the origin here. It's going to be way wider than the others, right? Something like this. Okay? And that's what I kind of thought it was going to look like. Once again, what it all comes down to, guys, is looking at this letter A. This letter A. What is right in front of the x squared? What is the x squared being multiplied by? If it's negative 1, it's just going to be a perfect reflection of the original one. That's my purple. If it's a number, it has an absolute value bigger than 1, right? Negative 2, negative 3, negative 7, negative 8, negative 10, negative 4, negative 2.5, negative 1.4, right? Anything that's further away has an absolute value greater than 1. It's going to be a vertical stretch, and it's going to be more narrow, right? Like the orange one. And then if it's a fraction between 0 and 1, right? If this letter A is negative 2/3, negative 1/4, negative 1/5, negative 3/8, negative 0.75, negative 0.66, negative 0.35, right? Any type of decimal or fraction that has an absolute value in between 0 and 1, it's going to be wider, and it's called a vertical shrink because we've taken this and we've shrunk it from having an absolute value of 1 to now it has an absolute value less than 1. Okay, I'm almost done. Apologize, this is getting kind of lengthy today. This is the last board. So I'm not even going to graph these. I just want to show you guys how you'll answer these questions because in our online stuff today, they're going to ask you to compare these to the original one. And I want to make sure you're confident on how to do that. So on every single one of these questions, I've switched up the letter. It's not a letter F anymore, right? This is our basic one, right? That has 1x squared. So if I just put it on here, it would look something like this. 2 times 2 is 4, so I need to go up to 4. So like here is the basic one, the parent one. the f of x equals 1x squared. That's the one right there. And now we're going to compare all these others to this one without actually graphing it. We can do that. Right? I switched up these letters to G, J, H, K. Don't let that bother you. They like to give you a variety of letters. Those really don't do anything, so don't have an anxiety attack whenever you see those letters switching out there in front of the parentheses. That really doesn't mean anything. It's just a different way to kind of label them, but it doesn't change anything about what we're doing. I keep hitting my phone today. I apologize. All right, this one, all we're looking at is these letters, or these numbers. The letter A, right, our ax squared. When the number is 2, right, anything bigger than 1, it's positive, so I know this opens up. So in my comparison, you really don't have to put that it opens up, but I know that. Since this is 2, it's bigger than the original, right? The original A is 1. If this A is bigger than that, I know it's going to be a vertical stretch. And if I want to be specific, I will say by a factor of 2. It's going to be twice as narrow as the original one. So like this one would be something like this, right? It's going to be twice as narrow, right? So this would be, I'm going to call this number 1 right here. This is number 1, right? It's going to be twice as narrow, and it's going to be labeled in our textbook as a vertical stretch by a factor of 2, because this is 2. The original, it's not really a slope, but it looks like where the slope usually is. The original slope is 1, this slope is 2, so it's going to be twice as narrow. It's going to be twice as compact. Okay. I didn't actually have to make the table, I just kind of freehanded that one. Now this one, you can see this guy right here, we got a couple things going on. It's negative. The fact that it's negative tells me that it opens down. The fancy math word for opens down means it's a reflection, right? This is a reflection over the x-axis. Because we had to take this and flip it, instead of going up, we got to flip it down here so it's pointing down. So it's a reflection. Now look at your A, your number right here. It's 1/2. Anytime your A number is a number that's in between 0 and 1, or 0 and -1, you know that it's going to be more wide open. This thing's going to be like this, right? It's going to be very wide compared to the original one. Like, look at my blue one. Look how narrow that is, and look how wide this one is. It's much wider than this. Right? That's very narrow. This is very wide. So this is going to be a vertical shrink, not a stretch. This is a shrink whenever the slope, whenever that letter A is in between 0 and 1, or 0 and -1. You call it a vertical shrink, and we're going to say by a factor of -1/2, right? Or you could just say 1/2. Honestly, I don't remember how our book puts it. 1/2 or -1/2. Either one is going to be what you're looking for. On the third one, I'll use red for this. We're back to positive, right? Now it's a decimal. Don't let that bother you. The fact that it's a decimal shouldn't be a big thing. It's still positive, so it still opens up. But look at what this number is. This number is 0.75. The original one, the parent has a letter A of 1. This is 0.75. This is less than 1. So if it's smaller than this is 1. 0.75 is less than 1. I know it's going to be more wide open, right? This is going to be a vertical shrink. Right? This is a shrink because we're less than 1. This is going to be more, well, I already did my other one in red. Let me switch to a different color here. Let's just maybe do black on this one. Since this is going to be more wide open. Oh, I guess I picked up green. Sorry about that. All right? So this is going to be like number 3 out here. All right? This is going to be more wide open than the original one. Kind of like makes an Under Armour logo with that one down there, and I didn't mean for it to do that, though. Okay, we have one grand finale. Down here, number 4, it says k of x equals -0.15. -0.15 means that it's going to open down because it's negative. So that's a reflection, right? This is a reflection in the x-axis, or over the x-axis. And here's another one that's a lot like letter J up here. This was -1/2. This is -0.15. On both of these, it is a decimal or a fraction that it's in between 0 and 1. And so this is another one that's going to be wider than the original one. It's going to be wider as well than the original one. So this is going to be a vertical shrink. Let me scoot my phone back. Vertical shrink. And I would say by a factor of 0.15. Right? Okay. I'm at 30 minutes, so I really need to stop this. I'm just going to put this board up here really quickly. One last review of what we did. Today we looked at parabolas, quadratic equations, quadratic functions. The most important thing we were looking at today is this number, the letter A, right? If the A is positive, it opens up. It's going to look like this. If the letter A is negative, it's going to open down. It's going to look like that. If A is bigger than 1, right? It's going to be a vertical stretch. It's going to be more narrow. It's going to be either closer together like this or closer together like this. If your letter A is in between 0 and 1, right? Like it's bigger than 0, but it's less than 1, or negative 1, right? It has an absolute value between 0 and 1. It's called a vertical shrink. These will be your fractions, right? They'll be more wide open, or they'll be more wide from side to side, right? Compared to those that are closer together. So these will be things like, these will be all your fractions: 1/2, 1/3, 2/5, 0.25, 0.70, right? And then these, when the A is bigger than 1, it'll be things like, 2, 4, 5, 3 1/3, right? It'll be all of those numbers. Okay, I'm going to put some questions on my Big Ideas Math website for my students. Hopefully you do the best you can. They're going to be kind of strange, but give it your best shot. And as always, email me if you have any questions or concerns. Thank you so much for watching. See ya.